All right, test. Okay. Hey everyone, I'm Jeremy. I'm a product manager on performance, and this is Mostafa. He is the TL for performance for all of Databricks. And today we're going to be giving a talk today about DBSQL serverless best practices and how to get the best performance. All right, so just kind of kicking this off, I want to just level set like how far we've come. We're going to announce some features that we've launched today. Also, we're going to go through what those best practices are, and then Mostafa is actually going to give a demo of how to use query profiles and do troubleshooting for best performance. All right, so I wanted to kind of bring everybody back to, hey, 15 years ago, what was it like? We haven't actually always been able to ask questions of our data. In 2010s, this was kind of the dark ages of data. Most questions couldn't be answered. If you had a scientist who had an insight and they wanted to go do some analysis, they really didn't have the ability to do it then. They could maybe do basic counts, but even that would have been difficult. Data engineering was very primitive. The tools were lacking. The hardware wasn't as good. And then Spark comes along, kind of changes this model. Fast forward 10 more years, 2020, and the data is now growing exponentially. You can see here, this is a horizontal line, so it becomes looking a lot more vertical in about a 20-year period. The questions become much harder, and then suddenly the costs started to explode. And then this new kind of economic wall emerged. Like we were looking at, you just couldn't even ask the questions, but now the new model is, hey, you could ask them, but it's really expensive, and it's going to cost a lot of money to do it. And the way that the traditional warehouses solve this is that they would just throw hardware at the problem. And this is a benchmark we run every year, and the cost curve looks the exact same for this particular warehouse. As the data grows, you can see it on the scale factor on the bottom, the costs go linear to exponential. But this isn't 2020, and the modern warehouse has to do many things well. It can't just do ETL, it can't just do BI, it's got to do a lot of things well. And so this is how we think about performance inside of DBSQL. We have this model, it's called the architecture of intelligence, and it really has one goal, and that's sublinear scaling. And it really is enabled, it's not enabled to just be fast, it's enabled for that economic breakthrough, to where you can ask any question of your data, and it gets cheaper instead of more expensive. Layer one is this data intelligence. It's where we learn the patterns, we recognize the data automatically for optimal access. Layer two is the things that are kind of the more, you hear about them more, this Photon and the query optimizer. And layer three is this intelligent auto-scaling layer where we can predict workloads, we can add and remove compute quickly, we can self-correct continuously. And just to kind of go through a little bit of how well this is working for us so far, this is what Ali showed on the keynote earlier today. DBSQL's, faster, less expensive across all scale factors, 1 terabyte and above. And as it gets bigger, as the data gets bigger, DBSQL is made to get more efficient as time goes. And that expands across all types of workloads. So you can see here, this is what we have something called the performance index internally. It's where the data scientists actually look at repeat queries over time to see if they're getting faster or slower. And what we can see is that across all workload types, BI, 28% faster, doing nothing. Like the query just gets faster. Exploratory, 31% faster across all workload types. The concurrency is getting better and better. DBSQL is made to go all the way up to 1,000 users and still continue to climb, keep steady the entire time. And then this is the model for how we scale. As I mentioned sublinearly before, this is that same benchmark I showed earlier. You can see DBSQL is continuing to scale horizontally while competitors are going vertical, 10x higher TCO in that benchmark. And now we've even expanded to AI functions. And AI functions we're continuing to increase the throughput. We've doubled down on that in the past year, 3x more throughput for the SQL AI functions than a competitive warehouse. But today, there's more. And this is what we announced earlier today. We're rolling out this 25% faster version of the warehouse, and it's new features that are doing it. I'm going to go into those, but it's the same SKU, it's the same price. You do nothing, and you're just going to get 25% faster on compute-bound workloads. And we did that through 2 breakthrough improvements that we launched today. The first one is something called predictive query execution, and the second one is photon vectorized shuffle. And I'll go through the details of it, but the high level here is that predictive query execution, it transforms these static query plans into continuously adapting systems, and photon vectorized shuffle is a new columnar shuffle engine. And so, PQE. All right, so the way PQE works, just 1 second, sorry, okay. The way PQE works is that it continuously monitors the plan in real time. Sorry, just 1 second, I think I'm missing a slide here. For some reason it's not loading the slide. But the way this works is PQE continuously monitors at a task level rather than just a stage level. This was, previously we used AQE. AQE is a way that we can adjust the query plan in real time. And the new way that we do this with PQE is that we can actually look asynchronously at the task level. We can adjust in real time, and we use an ML model, this intelligent evaluation section here, to replan the task as soon as we start noticing that something is going awry, something's not working the way it should. And the result of that is we get reduced compute waste and faster and more stable queries. And photon vectorized shuffle is, this is one where I had a lot of details on here, but the engineers really didn't want me to go into too much depth here and talk about the algorithms or anything. But as most of you probably know, shuffle is often the largest bottleneck. And if you think about it, CPUs are made to be extremely fast now. The latest CPUs are very quick, they're very parallel, and when the data has to move, the CPU stops. So this very fast engine suddenly has to stop to go get the data. And so the real insight here is that we drive the SIMD lanes. We skip the RAM, we keep the data as much as possible in the CPU, and this leads to us being very parallel, very fast, about 1.5x faster from our tests that we've. So now, getting into the best practices. The best practices for the best performance are really very simple now. We've made a lot of it default, and if you're using DBSQL serverless, a lot of this is just going to work out of the box. You don't have to do anything at all. But this command right here, create table cluster by auto, that is the #1 best practice that you can do. If you create the table like this, then you're going to be in a managed table. And I'm going to go into all the details of the whys and the whats. But create table will create a managed table. It's the fastest table type we have at Databricks. If you use cluster by auto, that will take care of all your partitioning, all your clustering out of the box. No, you don't have to do anything else. Predictive optimization is also rolling out by default now, so there's nothing to do on that side. All of this is just taken care of for you. So UC managed tables. A lot of people ask, okay, well, why are managed tables important? And the real insight here is that there's one metadata log in UC. And because there's one metadata log, every read and write, it hits that same central UC metadata log. And so the queries begin instantly. They don't have to call external systems. They don't have to do any checks. There's no chatter back and forth between the systems. And so it's about 80 to 90% less calls to external cloud storage when you go with a managed table. It's the fastest way. All of our data that we look at internally shows managed tables are the fastest way to have your data. So there's the slide that was missing from earlier. Somehow it got moved. I'll just skip that. So the auto liquid clustering is the next best practice. The data reorganizes itself. That is the real insight now. We've auto liquid clustering by default later in the year. But right now you still have to add that extra tag, cluster by auto. And what this does is it queries, as your queries go to Databricks, Databricks looks for the common query patterns, and then Databricks organizes your data. It automatically shuffles, or it automatically clusters it in the right way. And this is really good. I often hear when we talk to customers will say, hey, look, I know the right layout for my table. And for a few tables or 10 tables, even 20, 30 tables, that is the case. But once you start getting into lots of tables, Databricks, this is the type of thing that an ML model is good for. And Databricks is very good at looking at all your tables and clustering correctly. Next, I mentioned this earlier about predictive optimization. AI maintenance, it's just AI maintenance, right? It just works out of the box. It's 20x faster for these point lookup queries, and it can be up to 50% cheaper. And the way this works is PO looks at every read and write. It then auto clusters, it compacts, it vacuums. You don't have to do any manual optimize anymore. There's no scheduled maintenance windows. And this is really one of the big, most important pieces to having good performance, because once PO runs, it grabs the statistics of your data. When the statistics of your data are stored correctly, then the optimizers and Photon, they know what data they can skip. They know how the joins should be done. And so the queries get much faster as soon as you enable PO. It speeds up because you have less file, or you have file compaction where you can where you can trim the scans, you can cut storage. And then this only works now on high return on investment tables. So it doesn't just run if you never query the table. PO will only run when there's a high return for you. Now Mostafa is going to do a demo on query profiles.
Hello. Hey everybody, my name is Mostafa. I'm going to walk you guys through a demo. Also, luckily we're ahead of time, so I'm going to have plenty of time for questions, more than I thought. So, also, if any of you guys want to ask me a question while I'm doing this, like feel free, since we're almost like going to be wrapping up soon. So, let me hide this. So one of the key things around basically performance. So how do you guys ensure like you get good performance all the time? So someone like myself, I'm pretty sure many of you guys, I spend a lot of time authoring queries. I write a query trying to answer a business question, and sometimes basically this query is slow or basically behaving like not the way that I expected. So in DBSQL, also in DLT and as well as jobs, we have what we refer to as query profiles. I'm going to give you guys a tour about what a query profile is. So the main idea is basically you run a query. A query is trying to ask a business question. And in order to basically answer this business question, the query needs to go and read data, process rows, read partitions, et cetera, et cetera. And basically the query profiles. Hello? Yeah. Think of the query profile as basically an MRI for your query. It allows you to basically figure out where every second basically goes. So here it's showing some stats on I/O. It's showing some stats on files and partitions. It's also saying that, hey, this query has spilled 26 gigabytes, which is quite a bit large amount of data. And then if you see this chart, kind of looks like a query plan. You can kind of click on it. It's going to show you what we refer to as the DAG. But it's somewhat complex. It has a lot of boxes here and there. If you're trying to find what the bottleneck is, we try to basically simplify this as much as possible. You see this section here, see longest operation for this query. And it says like this grouping act took equivalent of 11 hours. So that we have threading in our system. So these are not actual work clock hours, these are actual work hours. Hello? Okay. So why is this taking a long time? And that's kind of quite a difficult question. Like I'm a performance engineer. I've been doing this for 2 decades. It's hard to expect every person to kind of know exactly how to read these and how to interpret them. But if I try looking a little bit here, it shows, well, this is like processing 500 billion rows, although it was basically reading from both sides around like 1.6 million and 4.8 million here. So what are we doing at Databricks to make this easier and kind of like to make these debugging journey a little bit much easier? So we added this cool button, which we refer to as optimize. And basically all you have to do after your query finishes or even after your query is running, click optimize. And basically what ends up happening here is that we have an AI agent that basically think of it as your own performance engineer. That's basically going to be looking at the query profile that I just showed you. And it's going to be looking for what the bottlenecks are and basically summarize it in plain English. So basically here it says like you're reading that many files, pruning that many files. It's telling me like, okay, there's a very expensive operator that's doing the join and ag. And it's also suggesting that there is a join condition that I'm missing. So here it will show me the following. Like it's showing that I was missing a join condition causing this explosion of rows. So let's kind of try accepting this suggestion and see what happens. So the previous query was running at 13 minutes. I'm going to basically hit that. And now I have my new query with the join condition I was missing. So in many cases, I author queries, and sometimes I miss the right join condition or the right predicate. Let's run it. So previous one was 30 minutes. Let's run this. Sorry. Okay, that's not gonna work. Yeah, that's not gonna work. Okay, this one looks like it works, but basically the main idea here is basically the AI agent will be able to modify the query and basically give me a better query. And then one of the other things we could also basically, with this AI, it's also able to cite the profile. So basically, we here have citation. If you click at the query profile, it's going to basically help you explain like these discussions, like basically where is it coming from. Also, similarly, it's able also to basically say there's a table which is line item which is partitioned by L-ship date, and it's missing. It's basically missing. Hold on, where to go? That's not good. It's basically missing this L-ship date filter. So the main goal here, or the main idea here, is basically we want to empower every person that's authoring queries with these AI agents in order to basically make their queries faster and more efficient, and also like including some simple basic English explanation how to basically apply these.